All right, so the plan is now to implement a recurrent neural network with an LSTM as a classifier to classify texts. So this will be a many-to-one word RNN because we are going to read in texts and then we regard each word as a token in that sequence. So in this video, I'm going to outline the different steps that are necessary for that. And then in the next video, we will take a look at how that looks like in PyTorch. So now these slides won't be pretty, but I hope they will kind of convey the big picture that underlies the PyTorch implementation. So because we are talking about a classification task, we are talking about a many-to-one network here. So we have as input, for example, a sentence, and then the output is a class label. So that will be a class label prediction. For instance, we are going to take a look at a IMDB movie review dataset, and then we are going to predict whether the reviewer thinks that the movie is positive or negative. So, just to recap, this is a slide I've shown you in the very beginning of this lecture. So this is the classic approach for text classification using the so-called back-of-words model. I don't want to discuss this again because I already discussed this in an earlier video, but I wanted to highlight again that we are using the so-called vocabulary here. For the RNN, we are also going to use a vocabulary that is similar to this one. The only thing is that this part here will be different. So we won't have a design matrix as a input to the machine learning algorithm. We will have an embedding. So basically a word embedding. So this will be now in 4 different steps. So I'm trying to do it step by step because it can be a little bit complicated. So breaking it down into smaller steps might help understanding the process. And these steps are also approximately how we would implement them in PyTorch. So this is for the recurrent neural network now. So step 1 would be also building a vocabulary similar to the classic approach. So you can see the vocabulary here is quite similar to the vocabulary I've shown you here. So I added 2 things here. Unknown, this is for unknown words, and this is a padding for making sequences the same length. This will become clear later. But essentially, the vocabulary is also a vocabulary that consists of all the unique words that can be found in the training set. So if this is my training set here, the vocabulary contains all the unique words. It's a set of unique words, and it's mapping to integers here, as you can see. The order doesn't really matter. You can do it alphabetically, but any order is really fine. It doesn't really matter which order the vocabulary is. It's just a mapping dictionary. And so we have this vocabulary here. And then step 2 would be using this vocabulary to convert the training example texts to indices. So again, if on the left hand side, this is my training data set. Let's now use the vocabulary to convert it into these integer indices. Why are we doing this, by the way, in the first place? That is because machine learning algorithms like to work with numbers, right? Because we have matrix multiplications and so forth, and we can't do a matrix multiplication with letters or words, right? So we have to somehow get the inputs into a representation that is numeric, something that we can do math with. So let's focus maybe on the first training example here, x1. The first training example is the sentence, "The sun is shining." So using the vocabulary, we are now translating. So this is the first word, the is index 7. So for the integer representation here, so this is on the right hand side our integer representation of that sentence. So we are now adding the 7 here, right? Because that's how it goes here. Then for the second one, this is sun, we have 5. So this goes here, and then 5 here. The next one is this one more, shining. one goes here. All right, so now we have mapped everything to integers. And compared to the back of words model, we keep the order here. So the order here in the sentence is the same as this order here. Because, yeah, the RNN is a sequence model, and like we talked about in an earlier video, the order matters when we work with text. So why are there ... and 10 here? So let's consider first the other sequences. So training example 2 and training example 3 here. So if we convert them to, you see that example 2 has 4 words, example 1 has 4 words. So we have 4 words, but sentence 3 has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 words actually. It's a much longer sentence. And because what we usually do is we arrange things in a batch, we would have to, we want to make everything the same length. So if I have, let's say, a batch, this is really for efficiency purposes, and we have in our first one here 4 words. Let me do it like this. 1, 2, 3, 4. Our second one is 4 words. We can't have like nothing. I mean, we can't have a matrix where there's nothing. That would not be a matrix anymore. Everything has to be in a matrix the same length. So we have to put some values here. And these are our padding values. These are basically, placeholders in a sense. So we are putting placeholders here to make everything the same size as this last one here. So this is really, it's not really necessary if we had an RNN where we only feed one training example at a time. But if we want to feed them as a batch, then it would be necessary because, there is a matrix multiplication at some point, and for that we have to have everything the same length. All right, but moving on. So let's now say we have our training set converted into these integers. If I go back one more time, let's now consider these that we have converted. So this was step 2. Let's now go to step 3, that is converting these indices to a one-hot representation. So this one here, this is our sentence. We are only taking a look at one sentence here, only one training example, just for keeping things smaller here, otherwise they won't fit onto the slide. So let's only focus on this training example, the first one. So this goes then into the integer representation. Why did I put it like 90 degree rotated? Just wanted to show you where we get these numbers from. 7, 5, 2, and then let's say 4. This is from the vocabulary. This is exactly the same that I've shown you before. So these are these numbers here. And then here the padding. So everything I'm showing you here, this is the integer representation from the previous slide. Now the new thing here is that we convert those to a one-hot representation. So how does it look like? So we would essentially have a matrix now where this is for one training example. So this matrix has the dimension here, the columns. This would be the dimension, the vocabulary size. And the rows would be the sentence length. So we have the sentence, it's a little bit hard to write this way, sentence length, and then the vocabulary size. And then for each word, so each row, this one would be essentially the first word, we would then look up create the one-hot representation. If our vocabulary size in this case is, it should be 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have a vocabulary size of 11. This is our index 10. This is index 0. So the first one is a 7 here. Let me use maybe a different color. Let me use the green. It's a 7. So we go 1, 2, 3, 4, 5, 6, 7. Second one is 5. So we go 1, 2, 3, 4, 5. The third one is a 2. So we go 0, 1, 2. And then let me see. I think okay, should have put this more to the right. But anyways, the same concept applies. Okay, so the 4 here, 0, 1, 2, 3, 4. All right, so this is how we create our one hot representation of that sentence. And then this is no wrong. I think I just copied and pasted the last one. These should be zeros. And the ones here are because of the padding. So these are our padded ones. So if you only focus on the input sentence, you can actually also ignore those. But these come from the fact that we did a padding earlier here to pad everything to the same size as sentence number 3. Okay, we have now our one hot representation. We have converted the text into integers, into an integer representation, and then text, then one hot. So that's this was step 2, step 3, and creating this vocabulary was step 1. All right, so the next step now is to go from the one hot representation into a representation that is containing real numbers, like decimal numbers, using a embedding matrix. This is a weight matrix, a specific type of weight matrix. But let's do it one at a time. So first, here is a recap of what I explained in the previous slides. So this is a recap. And we are now going to focus only in this overview here on one particular word. So let's consider we have this training example x1, and for this training example x1 we only focus on the first word for simplicity. So we built already this vocabulary. This was step 1. Let me use black for this. We built the vocabulary in step 1. In step 2, we learned how to convert the word together with the vocabulary into this integer representation. So step 3 was converting into the integer representation. Step 2 was converting it into integer representation. So we have this 7. Step 3 was actually the one hot encoding. So step 3 would be the one hot encoding. So this is what we had before. We are focusing only on this word the now, only this the. This is for simplicity. And I will show you on this slide how we convert this one hot encoding to a real number vector. So this one hot encoding here, I just copied this over to this position here. This is just copied over. And now we have this embedding matrix. This is a weight matrix that is initialized with random values, and this is updated during training, just like a hidden layer. And in fact, actually, the embedding can be implemented as, let's say, torch.nn.linear, a fully connected linear, or let me use a different color, fully connected layer. This is nothing new, it's just the regular weight layer. We don't need a bias for this one though. Okay, so here at the bottom, I'm now showing you how we go from this one hot vector into this embedded vector. So this is the hidden layer output, or we can also call it the embedded vector or word, or we can also call it the embedding. Actually, there are some dedicated methods for doing that. There's something called, for example, word to VEC, or there's also something called glove. These are models just trained to produce embeddings. So these are special models that can produce such embeddings, like this one, the real value vector. In this class, we're not doing this. This is an optional thing to do. So you could do this instead of learning the embedding. But here, the embedding matrix is essentially a part of this RNN. So here I'm just showing you the RNN, the many to one RNN. And the embedding matrix is just something that is used here. It's just a weight matrix that is learned, a matrix between the input and the hidden activations or hidden values. And really, this is just like in a regular perceptron. There's nothing really special about it. All right, so how do we get from this one hot vector with embedding matrix to the hidden layer output? Yeah, it's a matrix multiplication. So if you think of the one hot vector that we have from here, this is essentially, you can think of it as a 1 times v-dimensional matrix, where v is the vocabulary size. So if you think about the matrix multiplication, it would be 0 times 0.1 plus 0 times 1.1 plus 0 times 2.1 and so forth. There's only one value that is a 1 here. So the matrix multiplication between this vector here and this one, the first column, would be 7.1. And for the second one, if we multiply this one with the second column, this would be 2.5, 1.5, 1.5. So the output would be 7.1, 2.5, 1.5, 1.5. So this would be the embedded vector corresponding to this word the. So that's how we get from a word to actually a real vector that can then be used in the RNN. So this word would be then the input to this hidden activation. And if there was a previous time step, that two things as input here. One input would be really this vector here, and the other input would be the hidden state from t minus 2. If it's the first in the sequence, there is no input. So in this case, it's the first word of our sentence, so there won't be any t minus 1. It would be the first actually time step. So this would be actually the first time step. And this is how we input, let's say, a word into an RNN as a real value vector. All right, this is only one word though. Now we have to do the same thing. Well, let me go back one slide. We would have to do the same thing for sun is and shining. So this would be then a 4x4 matrix for the sentence. By the way, this is the embedding size. I just chose it to be 4 because, coincidentally it just fit well into this slide, but there's no correspondence between, let's say, the embedding size here and the sentence length. This is really independent. In fact, when you implement an RNN, you can choose the embedding size. So typically embedding sizes are something like 128 or 256 and so forth, but it really depends on how large the data set is and how difficult the classification task is. It has many different, it's just another hyperparameter essentially. It's similar to choosing a good batch size. It's also about choosing the embedding size. The embedding size is essentially a hidden layer. So like you experienced in the homework 3, it's just a hyperparameter to tune. Okay, so going one step further, now I'm telling you something that maybe makes you hate me. So steps 3 and 4 are actually not done in practice. So everything I've showed you here, from converting everything to a one hot vector and then getting this real value vector, this is not done in practice. I just explained it to you so that you understand what's going on, like conceptually. This is how we would do it conceptually, but in practice actually. So now it's of course a very complicated setup here, I understand. So you probably may have to watch this several times or think about it a little bit. It's not immediately obvious. But so this thing here, we discussed this just before. This is kind of inefficient, right? Because we have when we multiply this one with this first column, we have 0 times 0.1 plus 0 times 1.1 plus 0 times 2.1. If we have 11 values here, it's like 11 computations, but only one matters, right? So we do like 10 computations for nothing really here. And this is also a small vocabulary. We only have 11 different things in our vocabulary. If you have a real vocabulary, usually based on the training set, they are usually around, let's say, 200,000 words. Usually we make them smaller, let's say 20,000, but you have 20,000 words in the vocabulary, and then you have 19,999 wasted computations in each matrix multiplication. So to make this efficient, there is actually a torch.nn.embedding layer that just does the lookup. So instead of really doing the matrix multiplication between this one and this one, it just uses the index 7 here, and say, okay, just give me the value corresponding to index 7, look it up in the embedding matrix, and put it here. So in this way, we don't have to do the whole matrix multiplication. It's just a lookup table. So this is what I have here on the next slide. So there's actually this lookup function, or lookup approach called torch.nn.embedding. This is doing the same thing that we've done in steps 3 and 4, but it's more efficient because it's just looking up this value. So now let's consider the whole sentence again. So sentence number 1, the sun is shining. So in step 1, we created the vocabulary. In step 2, we converted the sentence to this integer representation or integer vector. Then in step 3, we converted this integer vector into a one-hot encoding, but we are not doing step 3 now. There's no step 3. Instead, we are taking this integer vector directly together with our embedding matrix. This is the exact same embedding matrix that I've shown you. And then we are looking up these values now. So for word 7, let's say this one. So for the word the, which corresponds to the 7 here, we are now looking up the row corresponding to 7. And this is then used here. This is our embedded sentence for the first training example. Then for the second word, sun, sun should be here, 5. We look it up here, we put it here. Then next one is, this is 2. Looking it up, this one goes here. The last one, shining, shining is 4. This one goes here, and this one goes here. And the remaining ones are padding because we had one sentence that was longer than 4. So these remaining ones would be the padding. But yeah, this is how, actually this shouldn't be here. Erase this. So these for padding if we have a sentence that is longer than 4 words. But you can see now the matrix we have here is the embedding size times the sentence length. And this is for one training example. If we have more than one training example, of course we would have a batch size. We would have a tensor, a 3D tensor for considering the batch size as well. This will become more clear in the code example that I will show you. Do I have one more slide? Yeah. So, okay. So now I was showing you these different steps here from converting a sentence into this input to the hidden layers in the recurrent neural network. In the code example, we are going to work with this setup. We are doing exactly that for a specific data set. We will be working with this IMDB dataset. So this is just a binary classification dataset. It's a sentiment classification dataset. Sentiment just means like the perception, like whether something is emotionally positive or negative, like what's the sentiment of something. So this IMDB movie dataset comes from the internet website, the Internet Movie Database, and this contains ratings for movies. And the rating can be between, I think, 0 and 10. And the researchers here, you can find the dataset here, the researchers have prepared it such that I think maybe I kind of forgot, it's a long time ago since I took a look at the paper or the method where they proposed this dataset. So I think the movie reviews are from 0 to 10, but they only use 0 to 4 for negative, and 7 to 10 for positive. They don't use 5 and 6 because it's ambiguous. They only use these, and they refer to them as highly polar movie reviews. So anything with a rating between 0 and 4 is considered negative, and anything between 7 and 10 is considered positive. And they have 25,000 reviews for training and 25,000 for testing. And here's just an example in a CSV file how the dataset looks like. So there's some text, and then there's a label 1 for positive, I think, and 0 for negative. Could also be the other way around. I actually can't tell based on reading this here. All right, so you have two sentiment labels, 0 and 1, and then this review text. And we are going to build a classifier that can classify these reviews. By the way, in the next video I will show you the code example for this IMDb movie review classification dataset. I just wanted to share this additional resource with you because I will only show you one video with code implementations or an example. I actually found this repository here which looks super helpful. It has more methods for RNN, LSTM classification, and also several tricks. There are some nice written tutorials, so there are more than these two. I just clipped this screenshot. But if you are interested in building RNNs for classification, I highly recommend this repository here. So there's also some library we are going to use. It's called Torch Text. So Torch Text is like Torch Vision, but for text. So there's PyTorch, and then there are libraries associated with that. Torch Vision is specifically for working with image data, and Torch Text is specifically for working with text data. There was recently a major update in Torch Text, so most or many things have changed a lot. And this tutorial, when I looked at it, it seemed like it was built for the original Torch Text. So now in 0.9, things have changed quite a bit. The old codes still work, but they are now considered legacy. So if you want to convert these codes here, I mean, technically you can just use them like they are. It works fine, but in the future, maybe in a few years, they may not work anymore. I don't know. I don't know what the exact plans are by Torch Text, whether they want to remove the legacy code. But if you're interested, there's also this migration tutorial, which explain what the things are that has changed between earlier version of Torch Text and Torch Text 0.9. So, but this is for this class entirely optional. It's just fine to use any of this if you are interested. So, and in the next in the next video, I will show you one of my codes for implementing RNN in PyTorch.